Hello everyone, so today we're going to go over section 3.10, derivatives of inverse trigonometric functions. We'll begin by considering the inverse trigonometric function y equals arc sine of x, and you can see here it is written in two different ways. Arc sine x spelled out is preferred because it avoids the unnecessary confusion with the reciprocal. So, if we write y equals arc sine of x, or just have the word spelled out, what we are saying is that sine y is equal to x, and that y is between negative pi over 2 and pi over 2. Okay, so here on the right we have the sine function y equals sine x in blue, and the arc sine function is in red. Actually, the way that it's graphed, this actually is just x equals to sine y, and you will notice that it is not a function. In order to make sure that it is a function, we need to restrict the range to be between negative pi over 2 and pi over 2. Also, you will also notice that these two functions are, of course, reciprocals of each other. You can see here, if I draw the line y equals x, they are reflections of one another over that line. Okay, so that's where this restriction comes from, is to make sure that we only consider the middle part of the arc sine now function. Okay, so if we are to find the derivative of the arc sine of x, we are going to use implicit differentiation. So first things first, we're going to write it as sine y is equal to x. Okay, and again, we're going to place the restriction in place so that it is going to be relevant later. So we're going to write it down right now. Again, y is going to be between negative pi over 2 and pi over 2. Okay, so it says to use implicit differentiation, so let's go ahead and do that. The derivative of sine y is cosine y. The derivative is in terms of x, so we have a factor of dy dx. And the derivative of x, of course, is just 1 in terms of x. So if you were to rearrange this, you simply get dy dx is equal to 1 over cosine y. The problem here is that it's not particularly useful because it is derivative in terms of y, but it is a function in terms of x, so that's not the best. Let's see what we can do here. So if we continue, notice that all the trig identities still apply. So we have cosine square y plus sine square y is equal to 1, the Pythagorean identity. We can subtract both sides by sine square y. So cosine square y is equal to 1 minus sine square y. Now, we can take the square root of both sides. So we get cosine y is equal to positive or negative, and then the square root of 1 minus sine y squared. And it's still not super useful yet. But now our range restriction is going to come in, because if y is between negative pi over 2 and pi over 2, then cosine y is going to be greater than or equal to 0. And how do we know that? Well, if we just look at the graph of x equals cosine y here, you notice that between y equals negative pi over 2 and positive pi over 2, cosine y is greater than or equal to 0. Okay, so going back to what we have here, then that means that cosine y, because of the range restriction, is only equal to the positive square root. So 1 minus sine square y. So that's a little bit better, but you still have the problem of everything being in terms of y. However, you notice that at the beginning we had sine y is equal to x. That means cosine y is equal to the square root of 1 minus sine square y, but it is also equal to 1 minus x squared. And that we can write in terms of just x. Okay, that means what we can do here on the left is to write this derivative y prime as simply 1 over the square root of 1 minus x squared, which is good. Now we have a derivative in terms of just the variable x, which is much more useful. Okay, so we can do the same thing with other arc sine, so other than arc sine, so other inverse trigonometric functions as well. We're just going to do one more. Here we have y equals arc tangent. Okay, it's going to do the same thing. We're going to rewrite this just as before as tangent y is equal to x. Again, we're going to use implicit differentiation, so the derivative of tangent y, of course, is secant square y. Then we have dy dx. And the right-hand side, we just have 1, just like before. Okay, so of course, then the derivative, dy over dx, is going to be equal to 1 over secant square y. Okay. Now, the Pythagorean identity that we used earlier, and that is cosine square y plus sine square y equals 1, we'll be using that again. But you'll notice that it doesn't contain any secant squares or tangents. So we are going to divide both sides by cosine square y. So now we get 1 plus tangent square y is equal to secant square y. Okay. So if we go back to the derivative on the left-hand side, then dy dx is equal to 1 over 1 plus tangent square y. Okay, but of course tangent square y is the same thing as x squared. We're going to use the same trick as the last example. So finally, y prime is going to be equal to simply 1 over 1 plus x squared. Okay. The same kind of technique can be applied to the rest of the trig ratio. So there will be 6 different inverse trigonometric functions and their derivative. This will be given in a table on the next page. Let's continue then. All right, we're going to differentiate y equals 1 over arc sine x, and then differentiate f of x equals to x arc tangent square root of x. So we're going to have to use some chain rules here. Let's see. First one, we simply have y equals to arc sine x to the negative 1 power. So if we are to take the derivative, then we have negative arc sine x 2 power, of course, using the power rule. Then the chain rule means we take the derivative of arc sine, which is going to give us 1 over the square root of 1 minus x squared, which is what we saw on the last page. Just like that. And then, since the first term has a negative exponent, so we can put everything kind of together, and we'll get y prime is equal to -1 over arc sine x squared, and then the square root of 1 minus x squared. Okay, so that's pretty much as simple as it's going to get for simplifying. Let's do one more then. We have the arc tangent expression. Let's look at what we have. Not much simplifying, so we're going to go and use the product rule in this case. So f prime of x is going to be equal to arc tangent square root of x. Since we take the derivative of x and we get 1. And then we're going to leave the x and then take the derivative of the arc tangent part. So that will give us 1 over square root of x squared. And then the chain rule, which means we have to take the derivative of square root of x. That will give us 1/2 x to the -1/2 power. Okay, so let's see. Next part, then we have still arc tangent. There's no real way to simplify the arc tangent square root of x component. And then second part, we'll have, let's see here, x from here in the numerator, and then 2 from the 1/2, and then we have 1 plus x, and then the square root of x. Okay. So aside from that, the only other thing you can really do is to rewrite x as root x times root x. That way we can simplify the expression a little bit more, and we will have arc tangent square root of x plus, and the last part here, the square root of x over 2, 1 plus x. Okay, and that's it. So, for the inverse trigonometric functions, again, there are 6 different derivatives. They are provided for you right here in this table. And again, you're going to use these new derivatives in conjunction with your product rule, quotient rule, chain rule that we have learned previously to find new derivatives. And that's it for today. Thank you for listening.